In this course, you are going to be working with mathematical objects and performing operations with those mathematical objects. Now, the way I phrased this last statement sounds somewhat abstract, but technically speaking, this is something you have been doing since you first learned math way back in grade school. The mathematical objects that you worked with were the numbers, and the operations you performed with those mathematical objects included addition and multiplication. Addition is an operation where you take some numbers and the sum of those numbers is the answer that you want when you perform the operation called addition. Multiplication is an operation where you take the product of some numbers. So performing operations using mathematical objects is something you've been doing for a very long time. In this course, beyond just using numbers, beyond just using scalar quantities, we work with vector quantities, and vectors are a more exotic type of mathematical object than scalar quantities. As a consequence of this, there is more than one way to perform multiplication with vector quantities. One type of multiplication with a vector we could work with is multiplying a scalar by a vector. This is a type of multiplication that we are going to work with explicitly very soon. Another type of vector multiplication is known as the dot product, or often referred to in math as the inner product. In this case, you take two vectors, you multiply them together following a certain rule, and you get just a number out as your answer. Another type of vector multiplication, you take two vectors, you follow a certain rule to multiply them, and you get a vector as your answer. And this is referred to as the cross product in physics. Now, the only type of vector multiplication we're going to explicitly work with in this course is multiplication by a scalar. We technically will encounter dot product and cross product in this course, but we're not going to explicitly point it out that we're encountering it here. So, as an example of how do we multiply a vector by a scalar, let's suppose vector A has components ax and ay, and let's say q is some scalar quantity. The product of q times a will describe a new vector. So you multiply a scalar by a vector, you get a vector out as your answer. Sometimes this vector is going to have its own symbol associated with it. An example that we're going to see in the future in this course is if you multiply mass times velocity, mass is a scalar, velocity is a vector, you get momentum, and momentum is given its own symbol. It's designated with vector p. The rule for multiplying a vector and a scalar is when you multiply a vector by a scalar, each component of that vector is individually multiplied by the scalar quantity. So to demonstrate this idea, let's suppose we have a vector A. Vector A has horizontal component negative 0.5 and vertical component 2. If we multiply vector A by the scalar number 3, pause the video, think about it. What will multiplying vector A by 3 do to vector A? What do you expect vector A to look like after we perform the scalar multiplication? So when we multiply vector A by 3, we multiply ax by 3 and we multiply ay by 3, and we will get our new horizontal and vertical components of a new vector. So when I multiply 3 times negative 0.5, I get negative 1.5. When I multiply 3 by 2, I get 6. So I get a new vector whose horizontal component is negative 1.5 and whose vertical component is 6. Now, if you look, you notice that 6 is 3 times larger than 2, and negative 1.5 is triple negative 0.5. If I were to draw this picture out, I would get a new vector that looks something like this. When I look at this vector, what did multiplying vector A by 3 do to the vector? Well, it essentially tripled the magnitude of the vector. Notice that the orientation of the vector is unchanged. Vector A still points in the exact same direction, but multiplying by 3 stretched it so it is now triple its length. And this rule is going to apply in general for any scalar multiplication. Whenever you multiply a vector by a scalar, you will either stretch or squeeze that vector. If you multiply a vector by a number greater than 1, you're going to stretch that vector out. If you multiply that vector by a number between 0 and 1, you're going to squeeze or shrink that vector down. But in all of these cases I mentioned, multiplying between 0 and 1 or multiplying between 1 and infinity, the vector always still points in the same direction. So as a second question, and I'm not going to answer this question after I propose it, I'll just move on. But if you want, you could think about it, you could talk about it in lab or recitation or office hours or wherever. What does multiplying a vector by a negative scalar do to that vector? So here are two vectors I drew on a picture. And my question to you, do these two vectors represent the same vector? Do they represent different vectors, or are they something else entirely? From the 3 blue, 1 brown video and some other things we have mentioned previously, we say any vectors that are parallel, meaning they are oriented in the same direction, they point in the same direction, and that have the same magnitude, are drawn with the same length in the figure, are considered to be the same vector. So this vector and this vector are the exact same vector for all our purposes. A consequence of this is if I have a vector, I am allowed to pick it up and move it around to somewhere else on my sheet, and it's still going to be considered the same vector. Also, as a result of this, all of these vectors are considered to represent the same physical vector that I might work with. On the other hand, these vectors I drew in red are not the same vectors as the vectors drawn in light blue. This vector, for example, points in the same direction, but it has a different magnitude, so it's considered a different vector. This vector has the same magnitude as the vectors in light blue, but it points in a different direction. This vector here, it points in a different direction. Even though the vectors at first look might look like they're kind of pointing in the same direction, I notice this arrow is in the positive x and positive y direction. This arrow is in the negative x and negative y direction. So these vectors would be considered anti-parallel. And set vectors like here are both have a different magnitude and a different direction. Sometimes vectors that describe different quantities can still be related to each other. So as an example, let's say this crystal has a length of 10 meters, and let's say this crystal points at an angle 75 degrees above the horizontal. Now, I'm just making these numbers up. I don't know what the real number is, but these numbers seem like a hand wavy, close enough to the real numbers. So I could say this crystal is oriented at a 75-degree angle and about 10 meters long, give or take. Now, in this example, I could also say, as a hand wavy argument, let's say this crystal grows at a rate of 1 centimeter every 100 years, and the crystal grows in a direction 75 degrees above the horizontal. So I could say this crystal grows about 0.01 centimeter per year. That would be 1 centimeter per 100 years. And again, it grows in a direction of 75 degrees. So in this example that I just mentioned, the rate of growth can kind of be thought of as being like a velocity vector. And the length of the crystal can kind of be thought of as being like a position vector. Now, since crystals will only grow in one direction, the velocity vector that describes this direction in which the crystal grows will end up being related to the magnitude of the position vector, how long the crystal is at a certain instant in time. And it will also be related to the direction of this position vector. So I'm just trying to say that vectors, even vectors describing different quantities, can have certain relationships among them.